last presentation of the day. I'll try to make it quick and sweet. Good evening, everyone. Thank you for having me here. My name is Gaurav Panwar. I work at New Mexico State University. I'm a PhD student, and I'm here to present our work on implicit denial of service attack in Indian and potential mitigations. So for an outline of my presentation, we have the motivation and the background of why Indian and where it fits, and the problem definition of the implicit denial of service attack, the potential mitigation solutions that we have proposed, and our observations and improvements that we see for this problem. As my fellow presenters from before have already, emphasized the idea of why Indian and how it fits into the future. Current network demands are not being met, and a lot of research has gone into proposing different techniques to mitigate the problems that we see in the network infrastructure for today. Multicast, caching, request aggregation. A lot of these techniques have been proposed in literature to try to cope with network traffic today. And the Indian, with its inherent advantages of having content which is name-based routing, decoupling the data from endpoints which are associated with IPs, and different routing conditions and flexibilities thereof, is a perfect fit, which makes sense. So Indian is definitely the way to look at it. Just to recap the decision flow of how an Indian's forwarding layer works, the strategy layer. Interest is received by a node on forwarder on a certain phase F. You check the content store because each node can potentially have a content store because of the cache name data. You can cache the data. If the interest is satisfied, if you have the data, you would forward it down to the node that requested it, and you're done. However, if you didn't have the data cached, you would check the PID entry, and this is the aggregation state. Where the node would aggregate the interest because it knows it's already forwarded the data request up to a higher node upstream. It would add the incoming phase to the PID entry, and it's done while it waits for the data to come back. And whenever the data comes, it would forward it to all the phases that it received the interest on. However, if there's no PID entry for the specific interest, you create a new entry in the PID, and you forward the data according to the interest according to the forwarding strategy that is on the current node. And then you'll be done, and whenever the data comes down, you forward it down to the phases that requested it. Looking at multicast in Indian, node could forward let's say it's node A, it wants to multicast its data. It could be some streaming scenario where you want to multicast for a P frame, or an I frame, which is more important than a P frame. You could multicast it just to make sure that in case there is some problem in the network on this side, you would at least receive it on the other side because it's more important data. Request aggregation, it reduces the network load. Let's say there's two nodes A and B. A's interest reaches router 2 first before B's interest does, and it's already forwarded up to R1, which is router 1. When B's interest reaches router 2, it's not forwarded up because router 2 knows that it's already it does have an existing PID entry, so it would not forward it up. And then whenever the data comes down, A and B both get the data without two interests going all the way to the producer. So this is an inherent feature in Indian which helps in reducing the traffic load. We also use unique nonces in Indian to eliminate loops or for detecting loops in the network. So let's say in this scenario, if router 1 decided to send the interest to router 3 in case there was a path on this side, and router 3 for some reason forwarded it up to R2, router 1 would detect that there's a loop in the network and could decide to either forward it somewhere else, or A should decide to forward it through another path. So these are essentially important parts of Indian, but in combination, there can be a case where you have an implicit denial of service scenario when all of these are combined. So just to give you an example, this is a toy example of a network, which is a contrived scenario, but this can occur. Implicitly, when there's an existing multicasting node which shares a router with a unicasting node, or even a potentially another multicasting node. So in this scenario, we're not considering any processing delays, it's just queuing propagation delays. So as the on the right side, I'm showing the PID table entries for router 1 and router 2. At 10 milliseconds, let's say the multicasting client sent both requests and multicasted it, which was client A. The nonces that you see, so in the PID entry, we're taking, just for simplicity, the names of the nodes are the nonces. So the interest reached router 2, router 1 has already forwarded it up to the producer and to the provider. At 15 milliseconds, router 2 gets B's interest and it aggregates it because it knows it's forwarded it up to router 1 already previously. But at 15 milliseconds, when router 1 gets the interest from which was sent from router 2 for node A, it would NAC it, which is showed in red. Essentially, router 1 detecting that there's some kind of a loop that it's received the interest, and it would drop it. And basically, when it drops it and sends the NAC down to router 2 eliminates the PID entry saying, okay, it's already been reached somehow and I've detected a loop here. So in this case, when router 1 receives the data for the interest from A, it would send the packet down, but B essentially got eliminated and there was node B never received the data and it would time out. This was basically B would either attempt again or would have to try on another interface if it needs to. So this is a situation which can occur. It can be implicit if it's an honest user, or explicit if it's a malicious user. For malicious user, the consumer would have, a multicasting consumer would have to predict what the unicasting or honest user is going to request and request it before them. But an honest consumer could also cause this if they're just multicasting, which could happen in a live streaming event where nodes can try to multicast interests which are for more important data. So some of the solutions that we propose for this scenario are either using unique nonces. So a multicasting node could decide to update the nonce on the strategy layer or the application layer to include unique nonces on each of the interests that it would be multicasting out. This would make the multicasted interest to appear unique in the network, so you would never NAC multicasted interest, and you would get the data on all interfaces that you multicasted on. Just to give you an example, in the scenario from before, when router A, the node A would multicast its interest, it would use the nonce A and A prime. Router 2 would basically aggregate B behind A prime, and router A would see A prime as a different nonce, so it would just aggregate the entry, and A would get data on both interfaces, and we would also end up getting the data. We did some back of the envelope calculations, some numerical analysis of this, and if you do this, you would see a lot of redundant deliveries, which is not ideal considering that you are getting data in so many interfaces and it would increase the network load. So here in an ideal case for this scenario, instead of getting back 120,000 packets back, you're seeing close to 200,000 or more, even up to more than 360,000. Some of the limitations of this solution would be you're significantly increasing redundant delivery, like we talked about. It's the worst case scenario for redundant delivery. You're increasing network load, obviously, because of it. You're also offloading the responsibility of mitigating this implicit denial of service on clients. So if you have a malicious user or a client who's not controlled on the strategy side, you can't basically dictate whether they're affecting other users or not. So this is not ideal if we want to deploy it as a solution. So we have another solution which is an improvement on this, which does not depend on the client base. It's basically a network core based strategy, so you would have to deploy this on your core routers instead of having to worry about clients deploying it on their endpoints. So you would use in-network retransmission and retransmit aggregated interests, which are NAC due to duplicate nonces. Just to give a flow diagram for how the strategy would work, when you receive a duplicate NAC, you check where the NAC is coming from, the incoming phase, which was an out record for the PID. You check the PID for interest, for the current interest, and if you have no aggregation, then you just delete the PID entry, which is what current strategies would do. And you forward the NAC down to the client side so that they have an idea that they shouldn't time out. They don't. It's more cleaner that way. They don't expect data in timeout. They know that they won't be receiving the data because of duplicate NAC. However, if there is an aggregated interest on the NAC client or the NAC router node, then you would find another nonce in the same aggregated PID entry and retry it up to the node that had originated the NAC towards you, and forward the NAC down again just for cleanliness sake, and you would be done. Just to give an example again on a similar network, let's say you have router 1 and 2 from the 4, you forward it. So in this case, you don't depend on the client. The client is still acting as the same client it was earlier. At 15 milliseconds when router 1 NACs router 2, router 2 would get the packet, NAC packet back at 20 milliseconds. It sees that it's got an aggregated entry, and in this case, it would retry with the second interest, which has a different nonce, which is nonce P, and send it up to the router 1. And whenever router 1 gets the interest, it would aggregate it, since it would see that it's not received this interest before. In this scenario, this is an ideal case where when the data comes back, A node receives it on one interface, and B node ends up receiving it and doesn't time out for the packet. So we simulated this in NDN-SIM. We randomly created a Barbasi scale-free network of about 40 clients, 80 clients, and 120 clients. 50% of these clients were multicasting, the other 50% were unicasting clients. And these are the network statistics that we see when we compare best route in the core and RRT on the core. The clients are all running the same strategy that we have in both scenarios, and RRT is basically the improved best route too. We are just doing the NAC handling with the duplicate nonce case. Essentially, it's the same strategy running in the core other than the NAC handling. So when we compare the number of the success rate, it's 100% success rate when we handle the NACs in the core, compared to when you don't, running just best route in the core, which doesn't handle the duplicate nonces. And it also shows the dependence. It's essentially a contrived scenario in some cases when you see toy networks, but it can happen in the network without the client trying to essentially doing an explicit denial of service. In terms of the number of interest in the network, we do see higher interest overhead in the network because the strategy would try to retry interest in the network. So it's essentially doing more, seeing more interest in the network when it retries. With BEST, we also see more packets delivered, redundant data. This is because obviously we're not timing out clients. We're delivering more data to the clients, but also we're delivering some redundant data where a client which was essentially receiving the data before would have aggregated behind some other clients which got timed out, and they would receive redundant data. But it's nearly impossible to eliminate redundant data completely unless you have some kind of node-to-node synchronization in terms of their PID entries. So we talked about this improvement. There are some cases where you have multiple retries if there's multiple levels of aggregation in the network, which can be improved upon by even further improving the strategy. Let's talk about those. We saw, what are the observations from this current scenario? We saw the delivery latency is similar because in this scenario, the latency of the NACking node up to the producer or the cache was more than the latency to just retry from the NAC node. So you were essentially retrying before the NACking node got the data back upstream and eliminating the case where the node would time out and have to retrieve data from the producer again. Also, in some of the cases, we see if there's multiple layers of levels of aggregation, the NAC node is trying multiple times because more than 2 or 3 times in case there's multiple interests that were aggregated higher than it that it would get NAC'd for. These retries can be eliminated. Just to show you an example of where this would occur, at 20 milliseconds, let's say router 1 has 3 interests already that are aggregated up, and it received the interest for A from phase 3, which was router from phase 3, essentially directly from A. So in this case, it would knock down to router 2, and router 2 would have to retry again with another interest that's already aggregated up. And then in the third try, it would essentially be able to aggregate just to make sure that the data for B comes to B and it doesn't get timed out. This is the case where we see sometimes you have to do multiple retries, and the previous solution works in this case too, but to eliminate these multiple retries, you can improve on the strategy from before by modifying the NAC that we're sending down to the node. The NAC can include the list of nonces that are currently aggregated. This would reduce the number of retries that a node downstream would have to do. So essentially in the previous case, the router 1 would send all the interests that are aggregated, all the nonces for the interests that are aggregated for the current NAC interest. And router 2 would be able to prune the tree. So in this case, you're eliminating multiple retries. You're also eliminating redundant data delivery, which might or might not be an objective. But this does require significant modification to the structure of how the forwarder works and the nonce packet structure and stuff. We didn't implement this solution because the current solution works with 100% success rate. Also, something to emphasize here is that the current solution can be adopted in any given strategy that is being deployed in the network. So it doesn't affect anything else. It doesn't affect the structure of how NFD works. It doesn't affect any existing forwarding strategy that you might have. If there's no duplicate nonces being seen in the network, then you wouldn't essentially trigger that part of the code, and it can be copy-pasted in all the forwarding strategies to eliminate, if there's ever a case, it would eliminate a lot of head-scratching with why a certain artifact in the network topology is being seen, because there might be multicasting clients that are also getting aggregated. So that's it, and I'm open for questions.
I'll steal Lisha's question. What's next?
We could do the implementation of the nonce packet that we talked about, modifying the nonce to include the number of pin entries that are in the current number of interests, and do a trade-off analysis of how much more interests that, because it has some other adverse effects too, because you're basically pruning the tree downstream, which could essentially have been eliminated, where you have multiple aggregated interests that wouldn't have been removed if you just retried with a different interest. You would deliver redundant data, which the current strategy does. You could eliminate that to reduce the network data load, where you're delivering data to a certain node on multiple interfaces. But that's also kind of, in some cases, you do want redundant delivery of data in case there's a problem in the faster path. So that depends on the application side, but this essentially doesn't adversely affect any clients and doesn't remove clients which were essentially going to get extra data.